So I think that we should start. So thank you very much for people to join, and thank you for your patience. So before start, so let's try to speak a little bit. That so we are very welcome to the 60th Open Seminar in Frontier of Nuclear Physics. This seminar series is organized by the Institute of Modern Physics, the key laboratory of nuclear physics and ion beam application of Fudan University, and the Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. It is supported by the programming of introducing talents of discipline to universities, the Journal of Nuclear Science and Techniques, and is live streaming on Coursera.com. So today it's our great pleasure to welcome Professor Tomofumi Nagae-san. So let me introduce our speakers a little bit. So Tomofumi Nagae-san is a senior professor at Kyoto University. He received the PhD at the University of Tokyo in 1968. After working at the University of Tokyo and Keikei, he joined Kyoto University and took the professorship since 2007. His primary research field is experimental hypernuclear and strange particle physics. He has published more than 70 few author papers and hundreds of collaboration papers. He served as a PRC editorial board member, a member of Science Council of Japan, and the president of the Physical Society of Japan. So now, please.
Okay, thank you very much for your introduction. My name is Tomo Nagae from Kyoto University. I'm very happy to have this seminar. Today, I want to discuss the present status of the hyperon-proton interactions. And also, I am scheduled to have another seminar in December 14th. On that occasion, I would discuss the JPAC Strangeness Physics program also. Okay, so today I would like to discuss the hyperon-nucleon interactions, what we are doing at the JPAC and also other places, and what we are now understanding on those hyperon-nucleon interactions. Starting from the introduction to hyperon physics and the nucleon-nucleon interactions. And also I discussed the experimental aspect of the hyperon-proton interaction, as well as theoretical models, which we are now going to establish somehow. As you may know, nowadays number of models for the hyperon-nucleon interaction exist nowadays, and it is very much exciting research field. Now it's related to the universe. I mean, physics of the neutron star is very close to our research field of hyperon-nucleon interaction. So let me start from the introduction of the hyperons. So as you know, we have in the flavor SU3 world, the ground states of baryons are baryon octet and decaplet. the spin 1/2 and spin 3/2 states are categorized like this. And we have proton and neutron in the baryon octet side. And also in this baryon octet, we have strangeness particles. Those are called hyperons historically. The lambda particle and the sigma particles, and also cascade or the Guzai particles. Those belongs to this baryon octet categorized like this one. And also we have baryon decaplet particles, delta and sigma star and cascade star, and as well as omega minus. So, and nucleon interaction is this neutron and proton. Just those two particles are involved, and we have a lot of hyperons. They are having strangeness degrees of freedom. Here I show you again the basic properties of the hyperon particles. The lightest hyperon is the lambda 1115 MeV. And because of the strangeness, the lifetime of the lambda is quite short. The C tau, the mean distance they travel with the speed of light is just about 8 centimeters. So in 8 centimeters, it decays into the nucleon and the pion. And those other hyperons are also decayed through the weak decay. The sigma particles, they are very short, 2.4 centimeters in mean lifetime distance. And cascade, we have two cascade minus and cascade 0. Those are the 5 centimeter and 9 centimeter. So that because of this short lifetime, we are not so easy to carry out the hyperon proton scattering experiment. In the case of nucleon interaction, we can have such a two-body nucleon scattering experiment rather easily, but for the case of hyperon, that's not so easy, which I a little bit more discuss more detail from now on. So to carry out the hyperon nucleon scattering experiment, that is ideal experimental situation to study the strange hyperon and nucleon interaction. But that is quite hard for the experimentalists to carry out. Why? Because in the case of the hyperon nucleon scattering experiment, we need a kind of the hyperon incident beam. Then we have a target of the proton, then which collide and react. We have a hyperon proton scattering experiment. So that the incident beam also target particles. We have those short lifetime hyperons involved, so that those hyperons just decay before they react with another baryon system, so that to have the large number of high statistics data, it's not so easy to carry on the hyperon proton scattering experiment inside the target. I mean, because of this mean decay lifetime of about few centimeters, every measurement for the beam and target should be done within those less than 10 centimeters. That is the problem. And also, if you use the thick target to overcome this problem, then another factor, you have energy loss struggling, so that not so good energy resolution can get through this kind of measurement. Here I just show you the example of the numbers which we required for the hyperon nucleon scattering experiment. Here you see in the case of the K- beam, that is the K- has a strange quark inside, so that we can easily inject it into the proton, but every around 7 meter long beam line, it decays into nucleon and pions and so on, so that most part of the half of the beam just decay if you use the 5 meter beam line. The most of the particles, beam particles, kaon, is just going to decay through the beam line transport. So it's not easy to get a high intensity beam. Okay, so now I move on to the two-body system, baryon-baryon interaction. That is, Yukawa proposed the interaction between two baryons, in his case, two nucleons, carried out through the exchange of the meson, pseudoscalar type meson, that is pion beam. And so by combining this N meson diagram shown here, we can get the interaction between the nucleon and this meson. So that so far, the most traditionally popular model for the baryon-baryon system is one boson exchange mechanism. So that in between the two baryons, the pi or the eta or the rho or omega and kaon. Those meson particles are exchanged through the two baryon systems, and that creates the attraction or the repulsion between the two baryon systems. This is the rough idea of the how we can get the baryon-baryon interaction model. And here I should stress that in the case of nucleon interaction, situation is quite different. I mean, experimentally very different. So that theoretical model building is also different in the baryon-baryon system. I mean, proton-proton and the proton-neutron scattering data events, those basic two-body data scattering events are available in the case of two nucleon case. About 6,000 elastic differential cross sections are available. Also, polarization related elementary scattering data is also more than 2,000 points we have, and also other data with very good statistical data is also about 1,700 events available, so that as you can see here, those very small point, that's the data point from the PP or PN scattering events. And so almost under this curve in red, that is the theoretical fitting results. And what we call this is the realistic nuclear force. What does it mean is the almost in these fitting, the statistical error coming from those high statistics two-body reaction. If you can just fit with this data, there is no more freedom to left, so that fitting chi-square is just about 1. So this is what we call the realistic nuclear force for the case of nucleon. This can be done because we have this 6,000 large number of two-body scattering data. So that compared to this situation in the nucleon case, here just one more page. So maybe you can say for the case of hyperon nucleon scattering, if it is that it can be measured, then the information for the hyperon nucleon interaction is or should be investigated in the same way for the nucleon interaction. But here, just SU3 flavor framework that 2-octet baryon interaction is classified to the singlet and 2-octet and 2-decaplet and 27-plet. So, and if you look at this diagram on the right-hand side, the NN force, which we have this realistic nuclear force, is just only 10 decaplet A and 27-plet S. In these just two categories, nucleon interactions exist in the SU3 flavor framework. So that it means that just knowing the nucleon case, it's not enough to understand other types of hyperon-related interactions. So that here I listed several important questions. So still we don't understand what is the origin of the repulsive core, which is exists in the nucleon case. But how about the hyperon-nucleon case? That is not known, not understood yet. And also the existence of the spin orbit force in the nuclear shell model, that is, typical nuclear phenomena. But this one also, we don't know what is the origin of the spin orbit force. Still, in the heavier system, and all the source of the spin orbit force, we still need some extra strength. And also in the theoretical side, the famous H dibaryon, that is from the theoretical side, this H dibaryon in singlet S state should be the have the attraction, very strong attraction should be in this singlet H dibaryon, and so far not observed is the theoretically not understood yet. Then also the statistics wise, here I show you all the hyperon-nucleon scattering data. No more data exists. And you can see that in the red part, those are the hyperon scattering event, but as compared to the blue ones, that's the NN scattering data, there is a significant difference between those two scattering elementary data. And measure those data were taken in the 1960s by using the bubble chamber, so that it's not so easy to improve so far. But now, because of the JPARC, we are going to get a new era to have the hyperon-nucleon interaction much better statistics, and also the momentum range of the data set is also quite improved. Those data will be soon available. And why we are excited in such a hypernuclear interaction is, it's a high density nuclear force. That's the what we would like to understand, such a high density matter, whether it exists or not inside of the neutron star. Neutron star is a peculiar star that radius is just 10 kilometers, but mass of the neutron star is 1.5 times solar mass, or recently there are two solar mass neutron stars, so that those we would like to have an answer whether this is true or not. I mean, strange particles exist inside such high density neutron star or not. Then recently such a mass measurement of the neutron star, and there are very high accurate measurement for the neutron star, and there is little bit problem we need to solve, which I would like to discuss later. But anyway, those high density matter case, the strangeness is a very important role they have for the neutron star to exist. Okay. This one I mentioned to you that usually use R and mass of the hyperon star, so that by using the several nuclear models, which is shown these curves, the mass and radius has some constraint coming from the hyperon-nucleon interaction. So here I should say that without any hyperon to exist inside the neutron star, its mass, it's hard to have the neutron star mass beyond 2 times the solar mass, so that we need some repulsion to explain this two solar mass neutron star to exist. We need to have the hyperon-nucleon or the 3-body force. Those extra, not 2-body force, is needed to have that more than 2 times the neutrons solar mass. Okay. this is just an example of the mass of the neutron star, and a lot of discussion, and some of them really exceeds the twice the solar mass. So that's the observation. And so at this moment, what we want to do next is to construct a realistic hypernuclear interaction, as well as realistic nuclear force. Just using the high intensity K-on beam at the J-park, we can improve the statistics of the hypernuclear scattering data, and which will be available in the coming years, and by including the hypernuclear, not only nuclear, but also hypernuclear data at the J-park, we want to understand the high density matter by using this realistic baryon interaction. That's in the right-hand side. As I said, in the case of nuclear, we have such a high realistic nuclear force model. But at this moment, hypernuclear case, still we don't have such a realistic baryon interaction model. So naively thinking that if we have a neutron star core, the density of this neutron star core should reach to the normal nuclear matter density, about 2 to 5 times the normal nuclear matter density, which is in this graph I put here. Beginning of the appearance of the strangeness, maybe at around 2 times normal nuclear matter density, and the strange particle like lambda may appear inside the neutron star, and going to the core of the star, neutron star, then density can go up more than 3 times rho zero. Then the heavier hyperon particles, sigma or the cascade, might appear inside in such a high density condition. So that's the present scenario of the physics of the neutron star core and the hyperonization of the nucleons inside the neutron star. And those are controlled by the strength of the hyperon nucleon force effect. Okay, so neutron star, that's very good and very interesting, but how it is connected to the hypernuclear spectroscopy. I just discuss a few slides on that. In the case of lambda particle, we have a potential inside the lambda hypernucleus. The lambda is bound, so that in the lambda bound region, we have a gamma ray transition, so that high precision gamma ray measurement can be done near the bottom of this potential lambda nucleus potential. So this one is only for the deeply bound systems. So at some nucleon emission threshold, gamma ray cannot be seen or measured in this region, but for the particle emission, these energy measuring these energy levels, we can get the whole information of the bound lambda system from the deeply bound ground state to near the threshold levels, so that we can, from these spectroscopic measurement, we can get the information of the hypernucleon interaction inside of the hypernucleus. So that's the way we have, and how we produce the hypernuclear is shown here. As I said, we use the kaon beam, which injects the strange quark into the lambda, or we can have a time reversal reaction, so that the pi k case, we have a SS bar production here, and those hypernuclear levels tells us the interaction of the spin-dependent part of the hypernucleus. This is a single particle orbit energy measurement so far done with pi k reaction. So this is a to the minus 2/3 plot, famous plot, so that in the nuclear matter limit, the attraction of the lambda is about 30 MeV. So this is quite sure all of us. So that this 30 MeV is the input to the neutron star mass. So that this 30 MeV attraction will bring in the neutron star or the hyperon appearance threshold mass is controlled. So 30 MeV deep in this case. Okay. So here is a compilation of the hypernuclear gamma ray measurement. Those arrows shows the major gamma ray transitions, and so that from these gamma ray measurement, we have we can get the information about the spin-dependent part of the reaction. Also, nowadays, in the S-shell lambda hypernuclei, here helium-4 lambda and hydrogen-4 lambda, those are the mirror hypernucleus nuclei, and that charge symmetry breaking is rather large, 350 keV, so that it's quite large number, so that people are now try to measure much more sensitive gamma ray measurement, and the test of the charge symmetry breaking will be done. Okay, so now I would like to show you some of the introduction to that next my seminar. That is a hadron hole extension project. At this moment, our JPAC hadron hole experimental hole is not the full designed area. I mean, in that JPAC construction started, we have a little bit short of the budget, so we designed and constructed just about half of the designed hadron hole, so that we are now discussing to enhance this JPAC hadron hole about the original size of the hole, so that we can almost double the space. That means at the same time we have a twice larger number of beam lines. So it's very effective to carry out the experiment. And our final goal should be to understand the strangeness degrees of freedom in the high density matter. That's this new hadron hole extended. We want to have such measurement, and I skip here, but so those measurement will be proposed and done. Okay. So this is the almost final of the talk here today. What is hadron puzzle is a better precision on the neutron star mass. We can have such a calculation by using the hypernuclear interaction model, which we construct. Also, there is a hope to have next gravitational wave from the neutron star merger event. Those will show us the very exciting data for the high density hadron matter. Sorry. I would like to summarize my talk. Still. Wait. I made too much slides here. Wait, I want to just show you the summary page. Okay. So here is the summary of my talk today. The hyperon-nucleon interaction potential, we are going to extend our baryon-baryon interaction model into SU3 with high intensity K- beam, so that those numbers, the precision might be improved in the coming years. So at this moment, lambda is 30 MeV attraction, and sigma has a repulsive potential, and cascade, that is nowadays we have a little bit of the information from the JPA. So this is also very important. And within the SU3 framework, the V cascade interaction is the last piece of experimental information, so that we want to finalize the measurement for the cascade. And hyperon puzzle should be, the answer should be provided from our society, research society. And now 3 body force is including the hyperon is quite interesting. And origin of the sigma p repulsion will be understood soon, I hope. And also cascade nucleon interaction is waiting for the experimental verification, whether it is attractive or repulsive. Thank you very much.
Thank you very much for a very comprehensive talk. So, although the time is limited, but I think that we still have leave sufficient time for discussion. So, yeah. So, if you have, I see that Peng from, so you can also open your, Peng, please open your mic, or people can also raise your hands. Yeah.
Okay, thank you very much for this nice overview talk. So you mentioned about the charge symmetry break for the hyperhydrogen 4 and hyperhelium 4. So they have the binding energy are different. So so my first question is, so could you give us a naive picture about what kind of physics behind this kind of charge symmetry break? So is this implies that the neutron lambda and the proton lambda interaction is different, or?
Yeah. Theoretically, it has been discussed with the lambda n sigma n coupling, mixing or coupling, lambda n sigma n. That the candidate, most promising candidate for the theorists to understand this, so that sigma lambda mass difference is about 75 MeV, but with this energy mass difference considered, we still can have a mixing effect of those lambda and sigma.
Okay, thank you.
Yeah. Of course.
You have a follow-up, or you have other question?
Oh no, thank you. I think this is this is really theoretical interpretation.
Okay.
Yes, thank you very much.
Oh, okay, thank you. So can I also have comments on this charge symmetry breakings that we just discussed? So yeah, the lambda and sigma mixing can kind of accommodate the large charge symmetry breaking, but the question is that actually in that calculation they give the value on the spin. I think that the spin dependent is different from the measurement, right?
Yeah.
And we are you probably you probably know that we in STAR we also have tried to measure this, but although the precision is limited, but our data tend to give the value for the ground state difference and the excited state difference. Actually, the number is almost the same, but with opposite side. So now you observe the value is 350 keV.
Yes.
That only for the excited state, right? But we see the ground state difference roughly 160, and excited state also is 160. But our error bar is very, very, very large.
I see.
Yeah. So I also have a question here regarding the charge symmetry breaking. So I wondering that, so for the experiment that actually performed at JPark, you measure the gamma ray. Actually is the gamma ray, the excitation energy, the transition energy. I think that the transition energy. So I want to ask that, can you also measure the H4 lambda for the binding energy of the H4 lambda? So because you inherit binding energy from the early emulsion data, right?
No. We have a new data.
You have new data.
Yeah. Rather new. No, so. Please wait. The data I showed you was JPark data.
This
which
2015, I think that, yeah.
And also this one.
This one. I think it's slide 18 or 17.
Yeah. Also, there is a discussion on the P-shell hypernuclear mirror nuclear energy levels, and they say that in the P-shell the interaction, the splitting is very small.
Okay.
And, so far, only in the S-shell hypernuclei, this is observed. Large symmetry breaking is observed. Well,
okay.
And
Next one.
next
one. Yeah, next one.
Yeah, this.
Yeah, this one. Yeah, this one.
This is no, this one. This one is a equal force charge symmetry breaking, and helium 4 lambda and hydrogen 4 lambda.
Okay.
So yeah, the large difference coming from this splitting of the 0 plus to 1 plus excited level.
Yes, yes. Okay, thank you. So I see there's also a question. So listen.
Hi, Nagae-san, thank you very much for this nice talk. Regarding in your conclusion, you mentioned there is a plan to measure the three-body interaction.
Mm.
Do you have already a specific experiment planned?
Oh, what experiment you mentioned?
Yeah, I mean, when you mentioned you want to measure the three-body lambda n interaction, have you designed some experiments? What kind of experiment you are talking?
We submitted the proposal, experimental proposal concerning the hadron hole extension.
Oh, so you already made a proposal.
Yeah, so in that proposal, we discussed by measuring the pi k energy levels with energy resolution of 100 keV. We may see the signal difference between the two-body reaction and the three-body reaction.
So I think you also mentioned in 14th of December, you will also give a talk. Are you going to talk about this experiment?
Oh, where?
I mean, in your next talk, you mentioned in the beginning, on 14th, you will also give a talk, right?
Yeah. Okay. Yes.
So I mean, are you going to talk about this experiment?
Yes. That's the main topics. One of the main topics. Yes.
Okay. Thank you very much. And I look forward to your talk.
Yeah.
Thank you.
Thank you. Can I have one more question? That
yes,
so
yes.
you have actually prepared the Kazai hypernuclei slide, but you didn't have time to discuss. So so regarding the Kiso event, and I want to ask that. So can you explore the lighter system? For example, the NNP and Kazai, I'm not sure if it exists or not, because this one actually we try in our experiment, but we don't have enough statistic.
Yeah. Maybe I can discuss it in the next seminar.
Okay.
Yeah. For the cascade hypernuclei, there is of course we will take the data for carbon target, but also
yes,
we would like to continue it to the lighter system.
That would be great. Yeah.
Yeah, the lithium, by using the lithium-6 or beryllium or boron, lighter than carbon target, would be the next step for us.
Okay, good to know. Thank you.
So I can discuss it in the next.
Okay, thank you.
Yeah.
I think it's late in Japan, and let me ask again if there is a question or comments from our audience. I think many people here, but so I see none. So thank you very much for this talk. So I conclude that the seminar is over, and then we're looking forward to your next seminar on December. Okay.
Okay.
Thank you very much.
Yeah, thank you.